welcome to the Deep Dive. Today we're taking a look at something really foundational to modern computing systems, especially servers and things that, absolutely need to stay running.
Right. We're talking about hot plugging.
Exactly. That magic trick of adding or removing hardware without having to power the whole thing down.
Yeah, specifically PCIe hot plugging.
Our source material for this is a pretty dense, comprehensive technical analysis. It's called PCI Express Native Hot Plug. Basically the rule book for this stuff.
That's right. And it really gets into the details of how and why this capability is, well, baked right into the PCIe architecture itself.
So our mission today, we want to pull out the key insights, understand what PCIe hot plug is, really, why it's designed in natively, how it works.
The hardware, the software involved.
Yeah, all the pieces.
Yeah.
And crucially, the differences in how systems handle, let's say, a planned removal versus a device just vanishing unexpectedly.
It's a feature we often just assume works, but making it reliable, that takes a lot of engineering under the hood.
Totally. So get ready to unpack the details behind swapping hardware without hitting that power switch. Okay, let's dig in.
So first things first, what exactly is hot plug in the PCIe world?
Right.
Well, simply put, it's just the ability to add or remove a hardware component, like an expansion card, while the system is fully powered up and running its operating system. No shutdown needed.
And the source emphasizes this idea of native support. How does that differ from, say, older ways of doing this, like with PCI?
Native is the key word here. It means this isn't some, bolted-on feature. You don't need special proprietary controllers like you often did with older PCI hot plug setups.
Oh.
The PCI spec explicitly says the architecture is designed from the get-go to natively support both hot add and hot removal.
So designed in from the ground floor. Not an afterthought.
Precisely. It's deeply integrated across the protocol layers, physical data link transaction layers, and it's defined in the configuration space that software uses.
Got it.
And this deep integration, well, that's what allows for standardized registers, standardized event handling, state machines. Basically, it fosters interoperability.
Which is huge, right? I mean, stuff from different vendors should ideally play nicely together.
That's the goal. It's not just a fancy slot. It's woven into how these devices talk to each other.
Okay, that makes sense. So thinking evolutionarily, why did PCIe prioritize this native support? What was pushing the need for better hot plugging?
Well, it really boils down to the demands of modern systems, servers, storage arrays, comms, platforms.
Things that need to stay online.
Absolutely. They require continuous availability. Downtime, even just adding a card or replacing a faulty one, it just got too expensive.
Right. The cost of taking a big server down. Ouch.
Exactly. So keeping systems running 24/7 was a huge driver. PCIe was aiming high for this third-gen I/O. Hot plug was core to that vision.
Beyond just keep it running, were there other specific goals?
Yeah, they wanted to support older solutions where needed, but the main goal was truly native hot plug, something that didn't need complex, non-standard sideband signals running alongside the main PCI lanes.
Okay.
They also wanted support for what's called asynchronous removal. We'll definitely get into that. It's tricky. And really importantly, a unified software model.
Ah, a unified software model. That sounds like music to an OS developer's ears.
Oh, it is. Standardizing how hot plug events and controls work simplifies OS and driver development massively. It leads to more predictable, stable behavior across different hardware.
And that ties back to the big picture goals.
Directly. Supports serviceability, easier maintenance, and scalability, easier expansion.
Okay, so the why is clear. Availability, easier management. Let's get into the core concepts then. What's hot plug fundamentally trying to achieve for the person operating the system?
The source highlights 4 key system-level goals. First, serviceability. Basically replace faulty parts without shutting down.
Less downtime for repairs. Got it.
Second, scalability or upgradability. Need more network ports, another GPU, just plug it in while it's running, dynamically adding I/O.
That's a big deal for growing systems.
Third, high availability and uptime. Directly minimizing downtime for any hardware changes. Keep things running.
Check.
And fourth, modularity. Makes systems easier to configure, reconfigure, build more flexible setups. And the spec provides what it calls a toolbox of mechanisms.
The toolbox?
Yeah, it's not just one rigid way to do it. It's a set of features that support different user models, different ways operators might interact with the system.
That makes sense. Different situations need different tools. Now, terminology. Hot add, hot remove seem clear.
Yeah.
But you mentioned different operational models. This feels important.
It is super important. It fundamentally changes how the system handles things. There are 2 main models, Orderly Removal Edition.
Okay, orderly sounds polite,
Yeah,
cooperative.
exactly. It's a coordinated dance between the user, the OS, and the hardware. Happens in a lockstep manner. Think safely remove hardware in Windows, but for, say, a network card inside a server. Ah, okay. So the user initiates it somehow.
Right, maybe presses a button or clicks something in the management UI. The OS gets the signal and starts preparing that device. Tells apps to stop using it, flushes caches, unloads the driver, basically makes it safe to remove.
It quiesces the device.
Perfect term. Once it's quiescent, the OS tells the hardware maybe a power controller, okay, cut the power to that slot. Then it updates the indicator lights to show it's safe. Then the user pulls the card.
So the OS is the traffic cop, ensuring everything stops safely before the physical action happens.
Exactly. It's all about graceful transitions, releasing resources properly. It's generally safer, simpler for the software to manage.
Okay, that's orderly. What about asynchronous removal? That sounds less orderly.
Much less. Async remover means the card is removed or its link goes down without any prior warning to the OS. It's uncoordinated.
Like someone just yanks the card out.
That's one way of surprise removal. Or it could be triggered internally by the system itself because of certain errors. Something called downstream port containment, or DPC, is a big one here. So the device just, poof, disappears from the system's perspective.
Pretty much. And that creates problems. What happens to data that was heading to that device? How do you stop the system from becoming unstable? How do you handle the inevitable errors?
Yeah, sounds messy.
It requires really robust hardware and software mechanisms to cope with that abrupt vanishing act and the potential mess it leaves behind.
So the core difference is preparation time. Orderly gives the OS time to clean up. Async forces the system to react instantly to a device just being gone.
You got it. Orderly is cleaner. Async demands resilience mechanisms that contain the damage and allow graceful recovery. And supporting async, especially with the robust features like BPC, is really vital for high availability systems that need to tolerate certain failures automatically.
That distinction is super clear now.
Okay.
Let's get into the toolbox itself, the actual building blocks. What are the main hardware and software pieces involved here?
Right. The source lays out a defined set of hardware bits and software interfaces working together. On the hardware side, the physical stuff is pretty visible.
Like those little LEDs on server backplanes.
Exactly. The indicators, they give crucial visual feedback. Typically, you'll have an attention indicator, often amber or yellow. It signals, hey, look here. Maybe there's a problem or an action is needed. Off is normal, steady on might mean a fault, and blinking. Blinking is often used to help you locate the specific slot you need to interact with in a crowded chassis.
Oh, the blinking locator light. That's genius, actually. So practical.
Totally. Then there's the power indicator, usually green. Tells you the power status. Off means power is off, you are permitted to remove. On means power is on, do not touch.
Okay.
And blinking usually means power is transitioning, so still not permitted. Software controls these, often with specific blink rates defined for consistency.
So they're not just status lights, they're safety signals. Safe to touch or hands off.
Precisely. A consistent, safe user experience is key. Beyond lights, you've got physical mechanisms. The manually operated retention latch, or MRL, that's the little lever or clip holding the card securely.
Right.
And there's usually an MRL sensor that detects if that latch is open or closed.
And that sensor actually does something. It's not just passive.
Oh, yeah. If the slot has a power controller, opening the MRL can automatically trigger power removal to the slot. It's a safety interlock, prevents you from pulling a powered card.
Ah, clever.
Some systems might add another layer, an electromechanical interlock, a physical lock that software has to release. Extra security against accidental or unauthorized removal. Its state is usually kept even if system power goes out.
So potentially multiple layers of safety latch, sensor, maybe even a software-controlled physical lock.
Exactly. Belt and suspenders approach for safety and data integrity. You also usually have an attention button, a physical button the user presses to signal they want to start a hot plug operation.
Okay.
And critically, the power controller itself. Software tells it to turn slot power on or off, but it's also smart.
Smart how?
It monitors the power going to the slot. If it detects a fault, like a short circuit, it automatically latches that fault state and cuts power itself, autonomously.
Like a tiny, intelligent circuit breaker for each slot.
Good analogy. It's vital for reliability in this electrically dynamic environment. Lastly, on the hardware-ish side, out-of-band presence detect, OOBPD.
Out of band.
Yeah, it's a way for the system to know if a card is physically present in the slot without needing the main PCIe link to be up and running. Super useful if the slot's powered off or the link just hasn't trained yet.
Gotcha. Okay, that's a fair bit of hardware. What about the software side of this toolbox?
Well, you need a software user interface, obviously, a GUI or command line tool provided by the OS or management software. Lets the user initiate things, check status, needs to handle multiple slots independently.
Makes sense.
There's also standardized slot numbering, a unique physical ID for each slot, usually based on chassis location. Software reads this from registers, makes managing specific slots much easier, especially for error reporting.
Right, so you know which slot has the issue.
Exactly. And that out-of-band presence detect we mentioned, it's not just hardware, it's a method software uses to check presence.
So it's this tight interplay between the physical bits and what the system software knows and controls. How does the system actually find out when something happens? Button press, card inserted, power fault.
That's managed by a structured hot plug event management system. Basically, hardware detects and latches the event, then notifies software to figure out what it means and what to do. Clear separation of duties, usually uses interrupts.
What kinds of events get tracked?
The downstream ports, the connectors on the system side, watch for several things. First, slot events. These relate to physical state or user actions, like attention button pressed, power fault detected, MRL sensor change state, or presence detect change state.
Okay.
When one happens, a status bit gets set in a register. If software has enabled notifications for that event type, it gets an alert.
What if things happen really fast, like a button gets jiggled?
Good point. The spec usually handles that.
Yeah.
Once a status bit is set for a specific event type on a slot, subsequent events of the same type are often ignored until software explicitly clears that status bit.
Debounce logic, essentially, prevents an event storm.
Exactly. Keeps the system from getting flooded. Then there are command-completed events. These just signal that a software command, like turn power on, has finished.
Simple enough.
And, really important, data link layer state change events. This tells software whether the underlying PCIe link is active or not. Absolutely critical after a hot add, so software knows when it can actually start talking to the new device.
Right, needs to know the connection is actually established.
Yeah. And the spec defines wait times. Like after the link comes up active, software might have to wait, say, 100 milliseconds before trying config access, giving the device time to settle. There are also timeouts. If the link doesn't train within, say, a second after power on is requested, software can assume something's wrong.
More built-in robustness.
Yeah.
Checks and balances. How does software get these notifications? You mentioned interrupts.
Right. There's a master enable bit for hot plug interrupts. Events can trigger traditional INTX interrupts. Those are level triggered. Or, more commonly now, MSI or MSIX messages, which are edge triggered. An interesting wrinkle is that hot plug events and power management events, PME, often share the same MSIMSIX vector.
So the interrupt handler gets triggered, but it doesn't immediately know why.
Exactly. The software handler has to then read the status registers to figure out, was that a hot plug thing or a power management thing? Saves interrupt resources, but adds a step for the software.
Got it.
Oh, and hot plug events can also potentially generate a wake-up event, a PME, to wake the system from sleep, if it's configured that way.
Okay, so hardware detects, log status, signals software via interrupts if enabled. Software handler wakes up, checks status registers, acts accordingly.
Yeah.
What are the key registers software looks at?
The main ones follow a standard PCIe pattern. Capability, control, and status registers, all part of the hot plug capability structure. The slot capabilities register tells you what physical hardware is actually present on this specific slot.
Like, does it have a button, a power controller, an interlock?
Exactly. Also flags like, is this slot hot plug capable? Does it support surprise removal, its power limit capabilities, and its unique physical slot number? It's the hardware's feature list.
And slot control.
That's where software takes charge. It has the enable bits for all the event notifications, control fields for turning indicators on-off, commanding the power controller, releasing the interlock. It's the software command center.
And status.
Slot status gives the current state MRL open-closed, card present via OOBPD, interlock, locked, unlocked. And crucially, it holds the latched status bits for any events that have occurred on that slot since software last cleared them.
So capability,
Yeah.
what's there, control, what software can do, status, what is happening or has happened. That structure makes sense, provides a consistent interface.
Absolutely. Standardized, predictable, regardless of who made the hardware.
Okay, let's loop back to those operational models, orderly versus async. Can you walk through the sequence for orderly hot plug again, maybe a bit more detail?
Sure. Orderly is the coordinated approach. For removal, it starts with a user request, button press, GUI click, whatever. The OS gets this. It then prepares the device, quiesces I/O, unmounts file systems, tells drivers to detach, releases resources. Only when the OS decides it's safe.
Right.
Does it command the power controller to cut power to the slot? Then it updates the indicators, turns the power light off, maybe blinks the attention light, signals, okay, safe to remove now. Then the user physically pulls the card.
That step-by-step OS managed process sounds much safer. And adding a device orderly.
User inserts the card into a slot prepared for it. System detects presence, OOB PD, or maybe initial link detection attempts. OS commands the power controller. Turn on power.
Okay.
Power stabilizes. Link training starts. Once the link is fully trained and active, that DLL state changed event fires. The OS waits the required minimum time, then starts configuring the device. Figures out what it is, assigns resources, loads drivers. Finally, it's available.
Okay. Orderly is clear. OS orchestrates everything. Now, async removal, the rough one. What are the biggest headaches it causes?
Fundamentally, it's a shock. The suddenness leads to potential data corruption if transactions were in flight. System instability if malformed data gets onto the fabric. Software getting stuck, waiting for responses from a device that's gone completion timeouts, and just generally making a mess of resource tracking and error reporting.
Sounds like a system crash waiting to happen. How does PCI stop that? What are the mechanisms?
Well, the source mentions hot plug surprise, HPS. It's a capability bit saying surprise removal might happen, but, and this is important, the spec now says HPS is deprecated for handling async hot plug.
Deprecated. So there's a better way.
Yes. The recommended mechanism is downstream port containment DPC.
DPC. Containment.
Yeah.
Sounds like it walls off the problem.
Exactly. DPC is an active containment feature. It gets triggered by certain uncorrectable errors, especially ones indicating the link just vanished unexpectedly below the port, the surprise down scenario.
And what does DPC do when triggered?
First, it automatically disables the link, forces it into electrical idle.
Why disable the link?
To stop the bleeding. Prevent any potentially garbage data malformed TLPs from propagating upstream from the faulty device or port into the rest of the system. It isolates the fault zone immediately.
Okay, that makes sense. Stop bad data from spreading. What else?
DPC also provides defined ways to handle requests that were already sent to the removed device. The port can generate error completions, like unsupported request, UR, or complete or abort, CA, and send those back to the original requester, basically saying, nope, that request failed. Some advanced root ports can even synthesize completions more gracefully.
So DPC doesn't just detect the surprise removal, it actively isolates the port and tries to provide a somewhat orderly failure notification for outstanding operations.
Precisely. The source calls it an architectural shift towards more active and integrated fault containment. Compared to just passively noting the device is gone, like HPS sort of did, DPC leaves the system in a much cleaner, more recoverable state. It's essential for high availability.
So that choice, orderly versus async, has huge implications. Orderly is simpler, user OS driven. Async needs robust hardware like DPC to handle failures gracefully and automatically.
That's the core trade-off. Enterprise systems really lean on async with DPC for that resilience.
Okay, let's shift gears slightly to a more advanced topic the source covers. System Firmware Intermediary, or SFI. What's the role of firmware here?
SFI is an optional feature, but it's formally defined. It basically allows the system firmware BIOS or UEFI to get involved in the hot plug process. It can act as a gatekeeper or an intermediary.
Intermediary between what? Hardware and OS?
Yeah. Often before the OS takes full control, or sometimes to manage what the OS sees about a device or event, it lets firmware handle platform-specific quirks or initialization steps.
How does it get involved? How does it know things are happening?
One way is through event signaling. SFI can configure certain hot plug events like presence detect changes, link state changes, or even device readiness notifications to be sent to the firmware instead of directly interrupting the OS. It uses correctable error core messages for this.
Wait, error messages? But these aren't necessarily errors, right?
Correct. The source is clear. When used for SFI, these error core messages are just a notification mechanism for firmware. They don't indicate an actual hardware error occurred. It's just repurposing an existing signaling path.
Okay, so firmware gets its own private channel for hot plug news. What about SFI downstream port filtering, DPF? What's firmware filtering?
DPF lets firmware tell a downstream port to essentially pretend the link below it is down, at least for certain types of traffic. Usually configuration requests from the OS, it can filter all requests or just config requests.
Why would firmware want to block the OS from configuring a device?
A key use case is preventing premature access. Maybe firmware needs to do some special setup on a newly added card before the OS starts poking around. DPF lets firmware hide the device from OS scans until it's done its platform-specific initialization, allows for firmware-first configuration.
But if the OS can't send config requests, how does the firmware configure the device itself?
That's the SFI configuration access method, or CAM. If SFI is present, CAM is there too. Firmware gets special registers. It writes the target address it wants to configure, then reads-writes a CAM data register. The port then sends a proxied config request on behalf of the firmware, bypassing the DPF filtering.
So firmware has a backdoor for configuration while keeping the OS out temporarily. Clever.
Exactly. SFI can also influence how the OS perceives device readiness. It can mask readiness messages, DRS, from the OS, or even generate a fake DRS message after firmware is done, potentially making the device appear ready to the OS faster than waiting for standard timeouts.
SFI sounds like a powerful tool for platform designers. Gives them a control layer between raw hardware events and the OS, useful for complex boot sequences or platform customization.
Definitely. It enhances robustness by letting firmware handle tricky bits before the OS gets involved, adds flexibility.
Let's talk power. Adding devices on the fly sounds like it could destabilize the system's power rails, if not managed carefully.
Oh, absolutely. Rapid changes in power draw are a big challenge. The PCIe spec includes mechanisms specifically for this: power budgeting and slot power limits.
Power budgeting first. What's the idea?
It's a framework for the system to manage and allocate its total available power, especially critical with hot plug, right? You plug in a new card, it immediately wants power. Budgeting ensures the system knows if it has enough power available in its overall budget before enabling the new device, prevents overloading the power supplies.
So the system tracks total capacity and allocates slices to devices.
Pretty much. Firmware or management software usually handles this. It needs to know the power requirements of existing devices and ensure there's headroom for newly added ones. Form factors for hot plug cards often mandate specific power behaviors too.
Is there finer control, like limiting power just for one specific slot?
Yes, that's slot power limit control. It lets software set a maximum power draw allowed for a device in a particular slot, more granular than the overall system budget.
How does the device find out about its limit?
The downstream port has registers for slot power limit value and scale. Platform software programs these based on what that slot can handle. Then, a specific PCIe message, set slot power limit, is sent across the link to the adapter.
And the adapter has to obey.
It's supposed to. The device driver and hardware are responsible for ensuring the card doesn't exceed the limit it received. The driver might complain if the limit is too low for it to function, though. There's also an interesting bit called auto slot power limit disable.
What does that do?
If software sets this bit, it stops the port from automatically sending that set slot power limit message right when the link comes up. This lets the host software manually control when devices power up fully, useful for staggering the power on sequence if you add multiple cards at once, managing the surge current.
So yeah, hot plug absolutely necessitates these power features. Budgeting, limits, messaging, all about keeping the power stable when loads change dynamically.
It's crucial for building dense, flexible systems that can handle a mix of devices without causing electrical problems.
What about resets? Devices need resetting sometimes, especially during a dam move. How does PCIe handle resets in a hot plug context?
Resets are fundamental for getting devices into known states. PCIe defines a few types. Broadly, conventional resets and function-level reset, FLR.
Conventional resets.
That includes fundamental reset and hot reset. Fundamental reset is a hardware thing, gets the port back to initial conditions. A cold reset happens when power is first applied, like to a newly hot added device. Warm reset is also hardware triggered, but the spec doesn't define a standard system-wide way to cause one.
And hot reset.
Hot reset is signaled in-band, using special patterns on the PCIe lanes themselves, TS1 ordered sets. It resets the link in the device downstream. Interestingly, forcing the link down to electrical idle either by software setting the link disable bit or automatically by DPC also causes a downstream hot reset.
Okay, so a hot added device gets power, undergoes fundamental reset.
Yeah.
How does the system know when it's actually ready to talk to?
After reset, the device starts link training the physical layer handshake to establish the connection speed and width. Eventually, it should reach the DL active state. But even then, software needs to wait.
Wait, why?
The spec mandates minimum wait times after reset or link training before software should try accessing the device's configuration space. Gives the device internal logic time to initialize fully. For example, maybe wait 100 meters after the link goes active. The device is also required to be responsive within a certain timeout, like 1 second after reset.
So those waits and timeouts prevent software from hitting a device that isn't quite ready yet.
Exactly. Though readiness notifications, DRS, can shortcut this, the device can signal "I'm ready now" earlier than the default timeout.
Got it. What about preparing for orderly removal? You mentioned function level reset, FLR, earlier.
Right. FLR is key for orderly removal prep. Unlike conventional resets that hit the link or whole device, FLR is software triggered and works at the function level. Remember, one card can have multiple PCI functions.
And the purpose of FLR for hot plug is?
Primarily quiescing operations. Before orderly removal, you need that function to stop doing work cleanly. FLR tells the function, stop I/O, flush pending stuff, clear internal state, get back to an initialized state. Data cleansing, basically, ensures no leftover transactions or state when the card is pulled.
So software targets a specific function and tells it to reset itself internally, cleanly.
Yep. Software sets a bit in the function's control register. It has to complete quickly, like within 100 meters. Importantly, FLR happens without affecting the PCIe link state itself. The link stays up. Software just needs to make sure things like pending interrupts are handled before initiating FLR.
So between fundamental reset on power-up, hot reset from link events, and software-driven FLR for cleanup, it's a whole coordinated system of resets and state management for the hot plug lifecycle.
Definitely. It's complex coordination. Hardware resets, link states, software waits, function-level resets, readiness checks, all working together.
The source appendix mentions an async hot plug reference model. It's non-normative, but what's its value?
Right. Non-normative means it's not a strict requirement for compliance, but it's there as highly recommended guidance. It's basically a best practices blueprint for software and firmware on how to handle the messy reality of asynchronous hot plug, especially focusing on DPC as the preferred way over the old HPS.
Why provide a blueprint if it's not required?
Because async events, by definition, are often tied to errors or unexpected situations, like DPC triggering on a surprise down error. They can leave system state ambiguous. This reference model gives developers a structured approach, how to set things up before an event, how to handle the notification, and how to recover and reconfigure afterwards.
Can you give it the gist of what it covers?
Sure. It talks about initial setup, deciding who owns error handling, OS or firmware, choosing the async mechanism, use DPC if you can, figuring out if a device is present initially, use OOBPD, waiting for readiness, DRS or timeouts, and configuring the port state based on whether you expect async removal or addition.
And handling the actual async removal.
It details the steps. Configuring error reporting, setting up interrupt handlers for DPC, link changes, PE changes, what the handler should do when notified, immediately stop access to the port. Logging errors, AERDPC logs, telling higher-level software the device is gone, verifying physical removal, OOBPD again, and finally, cleaning up the port to be ready for a future async add.
So a detailed checklist for detection, containment, reporting, cleanup, and async add.
Pretty much the reverse process, configuring an empty slot to detect insertion, the interrupt handler enabling power, waiting for link training and readiness, configuring the new adapter, setting that new adapter up for potential future async removal, and finally activating its driver.
It sounds like the model emphasizes a layered approach. Check physical presence, then link state, then config readiness, all while monitoring for errors like DVC triggers.
Exactly. Layered detection and recovery allows more precise diagnostics and tailored responses. That's why it's valuable guidance for building truly robust async-capable systems.
Wow. Okay, peeling back all these layers, PCIe native hot plug is way more intricate than just plugging something in.
Yeah, it's really not just about the physical act. It's this whole symphony of hardware detection, sensor states, power control, software coordination, timing rules, error containment.
We've definitely seen that toolbox in action. The indicators, the firmware intermediaries like SFI, and especially critical stuff like DPC, protecting the system from sudden removals.
And the payoff is huge, right? Increased availability, less downtime, easier upgrades, better fault tolerance, especially with DPC.
But clearly, getting it right is complex.
Yeah.
What are the big hurdles for system designers?
Well, the source points out a few. First, just the inherent implementation complexity of the toolbox itself, all the hardware, event logic, registers supporting both orderly and async, requires meticulous design.
And software.
Huge reliance on robust software support. OS, firmware, drivers all have to work together perfectly, interpreting events, managing states, resources, error recovery, especially for async.
Power seemed like a big one, too.
Absolutely. Power delivery and thermal management are critical. Dynamic loads need careful budgeting, slot power limits, thermal planning, and the physical design matters. Robust connectors, latches, signal integrity are essential for reliability.
And making sure vendor A's card works in vendor B's system.
Yeah, interoperability and testing is a massive challenge. Needs extensive testing across tons of scenarios to ensure it all works smoothly.
So it's clear. PCIe native hot plug is sophisticated critical tech, underpins modularity, serviceability, resilience. Complex to implement, but the standard provides that essential foundation.
Definitely. And the evolution, like pushing DPC over HPS, shows that ongoing focus on making these systems even more robust and reliable against the unexpected.
So the next time you see someone casually swap a card in a running server, maybe take a moment to appreciate that hidden ballet of hardware, firmware, and software, making it look easy. And here's maybe the really fascinating takeaway. This dive shows how even standard features hide layers upon layers of engineered complexity, all aimed at stability and flexibility. It really makes you wonder, what other everyday tech capabilities are built on similar depths of intricate design? What stands out to you?